Okay, I am, I guess. Let's see. Let's do this. So, I guess not many people really like want to join or something, so I'll just check the web for a second, and no, I guess not many. Well, not any, but not many. So, yeah, let's start. So things we are going to look at today are the following. First up, we start with homotopy of maps. But just in case someone needs a brief of like what we are doing, we are dealing with topological spaces and some maps between them. So homotopy of maps. Homotopy of maps. So we'll be looking at maps and define the notion of homotopy between them. So let's see. So what is first of all a homotopy? Let's define homotopy. In the context of maps between topological spaces. Later we'll see some homotopy of spaces themselves. For the maps between topological spaces, we'll take that a homotopy there are two major ways of seeing it. They are both equivalent, and they are both equally annoying in their own rights. So the first one, which is the more like traditional approach, would be to say a homotopy is a family of maps. Is a not just family, a continuous family. Continuous family of maps between from the same domain to the same codomain. A homotopy is a continuous family of maps FT from the same domain X to the same domain Y. That is one way of doing it. Where T is from like a generic closed interval on the real line. So usually it is the convention to take it as where T is from I, the generic interval, which by convention we will take to be 0, 1, but it could be actually anything, but it is convention to take it 0, 1, and we use the numbers 1 and 0 in that context to build like concatenation of maps, so it's best to stick with it. This is one of the many definitions. So it says a continuous family of maps. So what exactly is a continuous family of maps? We know what a continuous map is. A continuous map is for which an open set in the codomain has a pre-image which is also open in the domain. But what exactly is a continuous family of maps? Well, for that you can come to the other definition, which is a bit more precise about its terms, which is homotopy is a function, is just a continuous map, just a single continuous map f from x cross this generic interval I to y, when this x and this y are really the same as this x and this y. So yeah, that is what a homotopy is. It is a continuous map from a product space where we are producting our domain with the generic interval, and we are taking a map from it to the, let's say, y. And what relates these two definitions, that is, for any t in the interval, we can recover this map. We can recover this map from this map. For any t in the interval, we can have that f of x comma t equals f sub t of x for all x in the domain. That is what we are after, really. Okay, so there goes homotopy, which is again a single map from the product space. Just to look at an example, let's say we suppose we are collapsing. Let's say we are collapsing a circle to a line. That is what we are doing this time. So what are we doing? We collapse a circle, which I'm drawing like not like a circle, but yeah, they're the same thing topologically, aren't they? And we are collapsing that to a line by whatever means, let's say. Where's the curve option though? I don't see the curve. Anyway, by whatever map we have, let's say this map, which we, let's say, call f. So a homotopy would be a map from this circle, but we cross it with a line again. So what happens when we cross a circle with a line? We get a cylinder, don't we? We get a nice little cylinder here. Like that, I guess. Is that what a cylinder looks like? I guess it does. So, and here, over here, the bottom part of it. I don't really know how to draw the same shape again. I guess I will not draw this. I will maybe just copy this one out. Cheat a little bit. Yeah, there you go, a cylinder. So the way is to take a map from, let's say this is the starting map. Let's say we call this F0. And later on, we consider another map. Let's say like this, from here to here. And this to the same codomain, as we pointed out, that this map has to be, all of the maps from here to here have to be from the same domain to the same codomain. Let's say we call this map F1 for the endpoint of this interval, and this is F0. The homotopy, let's say the image of F0 looks like this on the line. Let's say it looks like this. The line takes it, we take the circle and map it onto this segment like that. And let's say in the course of the time, the homotopy basically moves this line around here to here, and in the end what we get is the image looks like this. So we basically squish a circle to the diameter and inject that diameter onto that line. So that is one way of doing it. Now this would be a nice small example of homotopy. We can look at better stuff for examples, but we are not really after examples or homotopy itself this time. We are doing the homotopy extension property, for which I have to define a huge number of other things. So up next, what comes to us is the concept of a deformation retraction. Deformation retraction. So what is a deformation retraction? It is a special kind of homotopy. In fact, it is a special kind of homotopy. It is just a homotopy between a map, the identity map on a space itself, and a retract. Oh yeah, I forgot to define one key thing before this, which is that when are two maps homotopic? Exactly when there is a map connecting them. So now we have a quick definition of homotopic maps. Imagine that is an O. Homotopic maps. Two maps, F and G, both from the same domain and codomain, are said to be homotopic. Now, that is really the word for this, and denoted F homotopic to Y. Let's see, denoted F, not the exactly equal sign, but this F homotopic to G. What happened? If there is, oh my god, there is a homotopy F from X cross I to Y such that the following holds, such that, oh wait, sorry, such that F, we ignore the first coordinate and we just look at the second coordinate, which is T, is not T, it is supposed to be 0. So the initial map is F, and the final map, this initial and final are not taken categorically, of course, just as a disclaimer. So we start with the map F and we end with the map G. If there is a homotopy like that, then we call the two maps F and G homotopic, denoted with that squiggly thing. So, time to define the deformation retraction. A deformation retraction is a homotopy between the identity map and the any retraction. So we will define all of what those things mean in terms of one thing itself. A deformation retraction is a homotopy F, again from X cross I, but now the codomain is also X itself. So it is a deformation retraction is a basically deformation of a space onto a subspace of itself. So that's why the codomain is the same space X. A homotopy, it is a homotopy such that the first map is the identity on X. So it does nothing. It just fixes every point. And for all t in the interval, like for every time, for every phase of this map, and for any point in that particular subspace, and choose a subspace X, a let's say, of X, and for any A, in this subspace A, we have that f of A comma t is A. So what is really happening is that throughout the time, initially the map fixes the entire space X, and as we move forward in time, the entire space X, of course, does not remain fixed. It gets more interesting than that. But there is the subspace A, which always stays fixed. So I have not really started the premise properly. A deformation retraction of a space X onto a subspace A. That is really what is going on. So we take a space X and a subspace A of it, and on that we define the concept of deformation retraction. Where does what come here? And for all things, for all moments in time, and for every point in that subspace A, and that point remains fixed. So throughout the time, that is to say that f comma t, if you restrict that to the subspace A, there is always the identity on A. That is another way of looking at it. So now, and there is another condition. This is the third condition. So how many conditions did we have? We had this condition, and we had then this condition, or this condition, and now for the third condition we have, and the image of the final map, so this time not t but instead of 1, is in A. So let's say we take a very bad notation, which is f of A comma 1, which is basically the image of the subspace A with the not really this, f of x comma 1, which is the image of the entire space X under the map, under the final map, that is necessarily equal to A, not a subspace. So this is a more tight condition than that. The previous one is not really entirely accurate. So the image of the final map is contained in the subspace. So what is really happening here is, we are choosing a space, let's say like this, and inside it we fix a subspace like this and call that A. This space is, let's say, X, and the deformation retraction is basically collapsing this space X onto that subspace A, collapsing it from all directions and collapsing it onto that subspace A. So like this, the entire space X gets mapped to this subspace A, which is also the image of the final map. So if you prefer this notation, then f1 of the entire space X. So that is what a deformation retraction is. You can of course deform some spaces to a single point. So let's say you have a space like this, which is basically a disk, and you can retract it to just a single point, like this. Yeah. And the definition Just like in the case of homotopy, we got the definition of a homotopic map. We don't get the definition of like retract spaces, but something very similar, which is to say that a space being a retract of another space. A space X is not just a retract, but a deformation retract. Probably mean the same thing, because retract is not really a word. Deformation retract of another space, let's say Y, if, what is the condition? If for some inclusion map J from X to Y. So this J is injective. It injects or includes X into Y for some this inclusion map Y. There is a deformation retraction. That's where this deformation retract comes in. There is a deformation retraction of Y onto this image subspace, which is J of X. So what this definition really means is that suppose there is a how to put it, so a circle, that was a rather poorly drawn circle. A circle is a deformation retract of an annulus, or a washer or ring, whatever that is called. A circle is a deformation retract of an annulus because you can have an inclusion map which takes this circle and includes that into the annulus like this around the hole, right? And then you can say that there is a deformation retraction of this annulus which contracts basically all of these sides and also through the middle. So this entire contraction takes place and the entire annulus gets mapped to that middle ring. So in that way, a circle is a deformation retract of an annulus. So that is really what is going on. So first of all, there exists for some inclusion. This statement that this works for some inclusion, not all inclusions, is important, because one can also include a circle into an annulus like this. You take the circle and inside the annulus you just put it here. You just put that circle into that somewhere here like this, and then one can show that this annulus does not really deformation retract onto that yellow space and the yellow image of the circle. So this does not really work to say that this inclusion does not work. Most of the time we will not see this inclusion map. Almost all of the sources and books, they only allow a subspace of that particular space. Let's say we are talking about we're talking about y, so they only allow a subspace of y to be a deformation retract of it. So if we phrase the definition like this, it will be necessary that x is a subspace of y, which is, well, not always the case. A circle can be a subspace of an annulus, but a circle is a circle. No, S1 is S1. An annulus is kind of like S1 cross. Annulus is basically a cylinder. When you are looking through a tube or something like that, if you literally take into account what is being projected onto your eye, that is really an annulus. You're seeing an annulus and thinking that you are looking through a tube or whatnot. So I'm talking about this thing. Suppose you are looking through a tube. Inside there is completely dark stuff, and outside there is stuff going on. So suppose you are looking into this tube, but you're now that you see the drawing, there's really a drawing of an annulus with this middle portion is the part of the world which is visible through the tube and all that. So yeah, there was quite an unnecessary rant right there. Anyway, on to more stuff, which is we covered what a homotopy is, homotopic maps, deformation retraction, some examples. So the definition that a space is a deformation retract. This is a keyword. This gets used all the time. I don't know, I forgot one definition, which is a contractible space. A contractible space is a space of which a point is a deformation retract. The space X is contractible if a point space as in just a singleton with the quite obvious topology on it. If the point space, let's say P, is a deformation retract of it, deformation retract of X. So that is what contractible space is. Okay, having done all that, are we missing something? Well, we are missing a lot of things, which is now we are to define the homotopy of spaces. That is a huge definition right there. Homotopy of spaces. On spaces, on maps, a homotopy was really just a continuous map. This, but for spaces, it is a bit more than that. It is not a continuous map. In fact, it is a relation. And please don't ask, there's nothing like a continuous relation. That thing does not exist. A homotopy of spaces. Two spaces, X and Y, are called homotopic or in some places homotopy equivalent. Homotopy equivalent if there is a map F from X to Y and a map G from y to x such that when you compose G with F, that is not equal to but homotopic to the identity on X, and when you compose F with G, that is also not equal but homotopic to the identity on Y. Now, of course, these are continuous maps. In topology, we only deal with continuous maps. And what does this definition, really mean or stand for? Is that, look, for before introducing homotopy and for getting into all that stuff, there is a notion of equivalence of two spaces in topology, which is that, which is that of an homeomorphism. So if we recall what the definition of a homeomorphism is, homeomorphism, or the definition of two space being homeomorphic, homeomorphism. So a homeomorphism was a function which is basically a bijection with a continuous inverse. Function f from x to y. Now, to put this in a more canonical language of a categorical isomorphism, we say this is a homeomorphism is nothing but an isomorphism in the category of topological spaces. So if we want to hear it that way, that is it. But in the language of mortals, we can say a homeomorphism is a function or a continuous map. Let's say I really prefer the word map in case of topology because it just sounds more stylish. A homeomorphism is a map f from x to y such that it has an inverse. There is another map G from y to x, and G being its inverse means G composed with F is equal to now to the identity map on X, and F composed with G is also equal to the identity map on Y. Now if you compare this definition of a homeomorphism to that of a homotopy or homotopy equivalence, we see that they're really the same. We are taking a map from x to y. It has some kind of an inverse under some relation. That is to say, the G composed with F is equivalent or related to the identity map on one space, and F composed with G is also equivalent to the identity map on the other space. And then we call it an equivalence relation of the two spaces themselves. That is their one thing. And here we write that x is homotopic to y, or homotopy equivalent to y, like this. And in the case of homeomorphic spaces, we used to write that x is homeomorphic to y, like this. So we are really after some kind of equivalence of spaces. That is what we are really doing here. And just like a homeomorphism is a map, similarly for homotopy of spaces, we also have the concept of homotopic map or an homotopy equivalence. That's where the name homotopy equivalence, this alternative name for two spaces being homotopic, comes from. So that is homotopy equivalence. Homotopy equivalence. Yeah. So just as in homomorphism is this, a homotopy equivalence is just the same thing. Homotopy equivalence is a map x to y, such that again there is a map such that there is a map G from y to x, such that G composed with F is homotopic to the identity on X, and F composed with G is also homotopic to the identity on Y. That is what really homotopy equivalence is. And as you can clearly see as a corollary of these definitions, two spaces are homotopic if and only if there is a homotopy equivalence map between them. So it doesn't really matter in which direction that equivalence is, because for any direction x to y, you get the other direction a map as well. So this is basically invertible under homotopy. That's what it really is. There is a homotopy equivalence between them, and usually this is something which is taken as a definition instead of a corollary or something, but I forgot to define homotopy equivalence maps before the homotopy of spaces. So this is a very nice equivalence statement. You can try and prove it if you want. It's really simple. Now what's up? Now we relate the fact that we talked about homotopy of maps, and that is this, and then we talked about deformation retraction. We saw how deformation retraction relates to the homotopy of maps. Now we saw homotopy of spaces. Now, is there a deformation retraction equivalent for the homotopy of spaces? And well, there is, and that is a fact that a space is always homotopic or homotopy equivalent to any of its many deformation retracts. That is almost the fact of the day, which is suppose let's put it that way. Suppose X is a deformation. Oh, my handwriting is getting really down. Deformation retraction of Y, then X is homotopic to Y. It is really key to not mix up the direction of the statement, because if X is a deformation retract of Y, then X is homotopic to Y. But it is not true, quite trivially, that two spaces which are homotopic are deformation retracts of each other or anything like that, anything remotely like that. So for a simple counterexample, that this statement is not reversible, or the converse of this statement is not true. Converse of this is not true. We can see this example, which is, let's say, a blob with two holes in it. So a space like this, let's say it is a main space, let's say Z. It has two deformation retracts. you can construct out of it two distinct deformation retracts, one of which looks like this just a cell, let's say, or a rectangle, or another blob with a line joining the two ends. This is a deformation retract. This is a deformation retract of the space. Let's call it X. And there is another possible deformation retract, which is this. So how do these things arise from this map set? So one way is that, let's say this was this color. You can say that this space can be embedded in it like this. Okay. And this space Y, let's say this color, this can be embedded in it like this. So from that picture we clearly see that the yellow space really retracts onto the green space, both the green space and also onto the red space. So we know that from this naming and whatever, this X is homotopic to Z and is homotopic to Y. Really. So we see that any two deformation retracts of the same space are homotopy equivalent, but you possibly for your life cannot find a deformation retract in either direction, from X to Y or from Y to X. It is just not possible. We have tried. It is not happening. But they are deformation retracts of the same space and therefore are homotopic, but there is no deformation retraction relation between them. So yeah, that is that. Okay, what else is to do? We got up to this. Now we will be looking at the homotopy extension property. So up next is the real stuff for which I started this stream and all that, but no one joined, is homotopy extension property. And we will be doing this just after a break. Okay, I guess we are back to it. So let's see. Homotopy extension property. Let's really get into this. What is the homotopy extension property? Of course, it is a property, and to be completely fair in terms of the logical nuances behind this, a homotopy extension property is a statement for space X and a subspace A of it. So this is really a proposition with these two parameters. What does this really say? A space X and a subspace of it, subspace A, this pair is this pair X comma A is said to have the homotopy extension property. If, now we got the definition of the property, if given any homotopy, let's say F, the homotopy is given on the subspace A, so A cross I to any space Y. If given any homotopy, when we say any homotopy, we also implicitly included that for any space Y and a homotopy of A onto Y, or like A to Y, given any homotopy like that, and what else is given? Another thing is given, and given any map. So this is not a homotopy per se, but this is just a map G from X to the same space Y. These two Y, these two are the same space. So that is the important part here. Given a homotopy from the subspace to the space Y, and any map G from the entire space to the same space Y, there is, okay, so there's one thing, not any map would work, such that there is a small condition in this, such that the condition is that f of a comma 0 is equal to g of a for all a in a. That is necessary. So the map G agrees with the first map of the homotopy F on whatever the subspace A is. So we'll look at a example in a second. Just let me get the statement right out here. Given any homotopy F on A and any map from G such that that map agrees with the homotopy on the subspace A, or rather agrees with the first map of the homotopy, there is a homotopy G from X to Y, so that this homotopy is basically an extension of the prior homotopy and also the map G. So that to say that this G, the first map of G is this map G, and at any point in time for any t in I and any a in a, let's say, we have that G of a comma t that really equals the prior homotopy f of a comma t. So this is the entire definition of when a space and its subspace A have the homotopy extension property. So this is really the entire statement of it. What does it really mean? This is that was a lot of words. So what this really means is that suppose given a space, okay, so we are mapping things to things. Let's first fix a space X. For this, I will choose this time this line, just a line, let's call this, let's call this X. And what is the subspace? For the subspace, I will choose just a point. This is really the subspace A. And where we are mapping this? We are mapping this to the, let's say, a disk or a two-dimensional plane or whatever. Let's call this R2. So we are mapping this to R2 and we choose a special map for it. So let's unpack the stuff. First of all, we are given a homotopy f from A to Y. What is that? So what is really a homotopy from a point? So from a point, any map means, you get the image to be a point as well. So there is this point here, and it is a homotopy, which is like, okay, so let's get an idea of what a homotopy of a point is. So this is a map. First of all, this is the map from A cross I. Now A is a single point, therefore A cross I is really just I. So this is essentially just a function. So this map F, since we know that A cross I is really homomorphic to just I, we get that this function F from A cross I to Y can really be just seen as another function, let's say F tilde, from I to Y. Now any continuous map from I to Y, it is known as a path. So the homotopy of this point is just a path inside this chosen space R2. So there goes the homotopy. And given any map, so given a map X to Y, which is, let's say, this map. I'm not naming the maps, that is problematic, but so this is the homotopy. What just happened? So let's say this is the homotopy F, and this is the map G. Let's say this map is like this, so something like this maybe. So this is really the space G of X. So as you can see, this map is basically an injection of X onto X into R2. So we are embedding X into R2. Injection as in, injections are called embeddings in topology. So so we are given this. And also we are satisfying the condition required of us, which is that the map G agrees with the homotopy. So what that really means is that when we map this point A, this one single point of A, under the map G, it really agrees with wherever the first map of this homotopy takes it. That is to say that this point is really on both this yellow path or yellow image, and also on this red path. Okay, so given this, there is a homotopy G from X to Y, from X cross I to Y, such that it contains both the G and it agrees with the previous homotopy F, which is if you if you try to do it, which that might be something like this. It might just be something like this. So this is the path. So this yellow or let's say let's color code this purple line. I'm not sure if it is visible on the screen though. Yeah, it is visible. This purple line is really the trajectory of this purple path. Okay, and for the rest of it, it is like just as you expect it. So I drew it really badly, to be frank. Yeah, I guess I should draw this again. The image of X looks more like this. Oh god, what happened? There's something traditional stuff going on. Okay, I cannot do that. I'm somehow not allowed to do that. So let's say the image is this. So the homotopy is more like this. These all are paths of individual points, the path they take. So this is kind of the homotopy in this case. Okay, so as it looks, if you try to look at a few more examples, you would see that really a homotopy is a way of packing a space onto some other space, if any of that makes sense. So suppose you are given let's look at another canonical space, which is a circle, a line and a circle. That is where all geometry began, and we are back to looking at lines and circles. So let's say take this circle, and not actually the circle, but that your space is actually a cylinder. Let's say your space is a cylinder like that. Okay, that looks horrible. Let's say your space looks like that. Whatever that thing is, a cylinder, you can imagine. Maybe I should draw it again. Anyway, drawing 101. We are drawing a cylinder today. Take a cylinder, take an oval or whatever like that. Take some lines around it, like that, I guess. Yeah, aligns with the center. Take another line, or actually be a bit lazy and just copy this line. Make a copy of that line and stick it right here. Okay, similarly make a copy of this top guy and stick it right here. There you go, cylinder. Perfect, first class. Now what we are doing is where do we map the cylinder? That is not an easy decision. Where should I map the cylinder? Let's see. I will map the cylinder. Where do I map the cylinder? That's a great question. Okay. Where should I map the cylinder? So I was looking, the reason why I'm looking at this example right here is that I want to look at something which is a bit more interesting than just a line, and comes within the drawing reach, comes well within my abilities to draw it. and also gives a lot of insight. So let's let's just look at uh, what do we look at even. Okay. Let's look at a non-example of this homotopy extension property. So that we relax one of the conditions and see that this does not really work out. Which condition should we relax? The obvious condition to relax is this condition right here, that the spaces have to agree. What the hell is that? So we can relax this condition and hope for something interesting or counterintuitive to pop out. So let's relax that condition. What we are doing here is that we will map the cylinder into a space like this. Check this out. The space we are taking this time is an annulus. It's like this. I'll make some room on the side. Okay, so how are we mapping the cylinder? First, let's fix a subspace of the cylinder. That subspace is going to be, of course, this, this oval right here. Not sure if I can copy that. Oh man. Okay, let's try a more interesting way. Change this change its color to red. Oh yeah, that works out. Or does it? It does not. Oh boy, why is that so horrible? Okay. First of all, just delete this. Just do with it. And then change its color. Okay, nice. And we are calling this space X, and this the subspace A, and this is the cylinder. The entire space, the cylinder is the entire space X. So now what we are going to do is map this subspace A around the loop of the annulus. So what we are going to do here is map this around the loop of the annulus. Yeah, that's just it. Take this and map it like this. So it is a loop around the annulus, which is something that looks like this. Let's say this is how we map that. So we also need to have a homotopy, and there is really no great way to have a homotopy in this situation. You know what? Scrap this example. This is doomed. We're not looking at this. Yeah, we're done with it. Never mind. So okay, what really comes after the definition of the homotopy extension property is to see who has the homotopy extension property, and in that case comes the good boy theorem, the fundamental theorem of it. The theorem says this pair of a space and subspace X comma A has the homotopy extension property, often written as HEP, if and only if. So this is a complete characterization of all pairs of spaces and subspaces, such that they have homotopy extension property if and only if a particular thing happens, which is, check this out, X cross 0 So this is just really a copy of X. Union that, really union that, not disjoint union, not make copies or whatever. Union that with A cross I. So this space X, not this space X, this space, this union of a copy of X and the square or rectangle, whatever, made by A, is a deformation retract of X cross I. So that is it. If you can take the space X cross I, or which is more commonly in a better way known as the cylinder on X, you can just take the cylinder on X and deform it. So it gives a deformation retract. You can deform it to X cross, basically a copy of X, which you can always do. That is easy. A cross I. So what is really going on? So here we are supposed to have a deformation retraction, that kind of action going from X cross I to this union, which is X cross 0 union A cross I. Now notice that this is really very easily possible. It is very easy to have a deformation retract like this. Easy to have a deformation retraction of X cross I to just a copy of X, because I is contractible. You can contract I to any point. So you contract I to the point just 0 and map X along with it. So that is really possible. So it is like really mapping this cylinder, taking this cylinder and squishing this down to the bottom circle. So that is possible. It is also easy. It is also not very hard to have a deformation retract of X cross I to A cross I. If X already deformation retracts onto A, this is a retraction or a deformation retraction. So if this happens, so let's say this square deformation retracts to this line right here, like that. That is because this line really retracts onto this point right here, and all we are doing is taking a cylinder on it. We are just suspending all of this. We are crossing all of this by I. That's basically the reason why this works out. So because it's easy to have this kind of retract and this kind of retract, we expect that it is easy to have a retraction which is like this. And in fact that is true, which is the content of the next theorem, which says, we get a theorem right after it, less of a theorem, more of a proposition, that any CW complex has this property, has the homotopy extension property. So that means for any CW complex X and any CW complex, as in any pair of a CW complex and a subcomplex like this. Any pair of a CW complex and its subcomplex has the homotopy extension property, which means in that way that for any CW complex, since a circle is a CW complex, imagine that is a circle, and a point is a CW complex, so the cylinder can really, so cylinder like this, it can really be deformation retracted onto a line with a circle. This line is this point cross I, and this circle is just the top thing, X. So yeah, that is another thing. So now we are going to try and prove the first theorem. I have not looked at the proof yet, so I will try to do it. I hope you guys try and do it. By you guys, I mean whatever hypothetical viewer is watching, because no one is watching. So yeah, okay. We are going to try and prove this. How are you going to prove it? It's okay. Let's do the reverse direction first. That we have a deformation retraction of F cross I to that union, and we want to, get the homotopy extension property proven. Suppose X cross I deformation retracts, deformation retracts onto this horrible thing, which is really just a never mind. Suppose it deformation retracts onto this. That is to say, there is a homotopy. Let's say that there is a retraction. For some retraction. This retraction is a technical term which basically means which is basically a continuous idempotent map, but that does not really help that much. This retraction X cross I onto well, yeah, we can do it. This retraction from X cross I to X cross I such that R square, which is R composed with R, that is equal to R. So it is idempotent map. And the image, the first image, so the R of X cross I is equal to this subspace. For some deformation retraction R like this, we have the identity on X cross I is homotopic to R. Okay, great. All nice. And suppose you are given now, suppose you are given a homotopy X, a homotopy F from X cross I, which is just continuous map F. At this point we are not treating homotopy like a family of maps. Given something like this, not X cross I but rather A cross I, suppose this, not suppose, this is given. Now given F like this and G from X to Y such that G of A equals F of A comma 0 for all A in A. Now given this, what can we do? How do you construct homotopy from here to here? So this is, this is your space. This is, let's say, A cross I to Y. This is A cross I, and what the hell? And this is a copy of X. And this is the union. X cross this union. I'm not really I don't really have much of an idea of what I'm doing right now. I'm just trying to get a proof anyhow. So we know that there is a map like this. There's not really an injection, okay? So we know that we have a map like this, which is basically a copy of G. Let's say G tilde. If you want, you can always be a bit more pedantic about things, which I like to be pedantic. I really do like to be pedantic. So as we can see, this is homeomorphism, and this map is G X to Y. So this map really has to be a copy of G, which is an exchange with a homeomorphism or something like that. We know that this contracts onto this. We are not sure if this contracts onto this, but we know that there is a map from this to this, which is this homotopy F, and we know that there is this thing right here, that this deformation retracts onto that space. So this retraction R can be really thought of as some kind of a surjection onto X. So this is a copy of R. Again, you can just inject this back, this injection J, and this would be the identity map injection type of thing. And okay, let's see what we got going here. This is not really easy, to be frank. I'm telling you, this is not really easy. So if we try to do something with this diagram right here. So we have this space, a copy of X, and we have A cross I, and this special condition in the definition of a homotopy, the homotopy extension property, this condition comes in here exactly because there is an intersection between where did it go? We account for this condition in that there is an intersection between these two things. The intersection is not really empty. That is easy to see if you take X to be like this. Let's say A is a point right here, and this is A cross I, and this is basically X cross 0. So the intersection is really this A cross 0. That is where really the intersection lies. So what we can do here is take this intersection. So let's see, we take this intersection A cross 0, right? Since 0 is a subspace of I, we can inject it here, J1. This is all canonical maps. So we really inject 0 into 0, 1 like this. So this is 0. this is 0. We really inject that to 0 comma 1 like this. We send 0 to 0. We don't do anything else. That is exactly what we are doing. And also we can have an injection right here, J2, and here we really are including this subspace A of whatever this is, X, into really where it belongs. So this is really this injection right here. So these are canonical injections. This is J2, this is J2, this is J1, and this is J1. Yeah. So this is what is going on. We do this injection of this A cross 0 point. Okay, it is probably a good idea to have an actual image in mind. The image I want to look at is the space X being this line, and A being this, and this is A cross I, this line. So this is A cross 0, and this is X cross 0. This is the image I'm really after, and therefore this thing right here is the entire X cross I. So we inject this A cross 0 into these two things. So inject it into X cross 0, and we inject A cross 0 into A cross I. And now what we are doing? Now what we can do is, so this really looks like this. You have this point A cross 0. We can repeat the diagram again, but let's get this clear. And we can inject this into this line by J1, which is, this line is A cross I, and again by J2, this injection, we can inject it onto this line, which is X cross 0, X cross 0. And now what we can do is, having these things right here, we can inject them again. Let's say this is J3, this is J4. We can inject them again. Inject into what? Inject into this. Inject into this X cross 0 union A cross I. And now we will see that this diagram commutes, that indeed J3 composed with J1, this injection right here, J3 composed with J1, that really equals this injection right here, which is J4 composed with J2, in that both of them send this point to this point. So this diagram really commutes. So okay, so far what did we do for ourselves? What we did for ourselves is, we have this space A cross 0. We injected it via J1 to A cross I. We injected it via J2 to X cross 0. And we injected both of them by these maps, J3 and J4, into this. And this diagram commutes, or so we claim. Okay, this looks really horrible. I should probably draw a better diagram. This is the traditional case of the commuting square. I'll try to draw my best. Not really strong in the arts, as you can see. Yeah, I'll call it today. This is X cross 0. This is A cross I, and this is X cross 0 union A cross I. And that's probably the best I can do right now. Anyway, so given this, and we know that there is this external space Y. I guess I should draw it a bit far away because there could be a lot of clutter going on here. First of all, we know that there is a map from X to this, or rather a copy of X. There is really a map from, this is a homeomorphic copy of X, right? X cross 0. That is indeed a homeomorphic copy of X. Let's see. Time to improve this. Yes, that is doable. This X cross. Oh god. Okay, nice. So because we have a map from X to Y, which is G, we have a copy of G. Let's say G dash. You could go ahead and call it G cross 0. I don't really mind, but no, I won't do that. There's already a lot of things going on. And also, there is this map from A cross I to Y, like this. The map in question is F. That is the homotopy we talked about. Now, because this space X cross 0 union with A cross Y is kind of like a fibered co-product, as you can see, and we also have the map from this intersection of the two spaces, which is, there's a kind of map from A cross 0 to Y, which is basically the initial map. It's, you can say it is G restricted to A, or a homeomorphic copy of G restricted to A. And also you can say that it is the first map, F comma 0. So we really do have this map. I know this picture right now really looks terrible, absolutely terrible, but I guess I can't help it. So what we wish to do here is that we wish to just we can just grab a map right here. Yeah, I guess that is probably the best thing we can do. Let's call this phi. So I claim that there is a map phi from X cross 0 union with A cross I, such that this entire diagram commutes. You see, this entire diagram commutes. That to say, first of all, such random things are disappearing. What does it mean to say that this diagram commutes? Is that first of all, through the right branch of this, if you restrict this map phi restricted to A cross I, that would really be equal to that homotopy F. Okay. I guess I don't really need to name the inclusions right here. They're canonical inclusions. You don't need name for them. And also, phi restricted to this copy of X right here, that would be equal to this copy of G. So this map really exists, and that is because this space right here this is a fibered co-product of these two spaces. So we are not really taking a co-product, that is the disjoint union of these two spaces. Instead, we are taking a fibered co-product, and the fibers are from these two maps, these two inclusions. And so really this is the commuting square, and that's why we were really after getting that commuting square. So after having gotten this commuting square and the fibered co-product, we can say that this map phi exists. And after this, we are really half done. This direction is really done, which is because there is this retraction R onto this, or at least if not R, if you want to be pedantic about it, it is a copy of R, where we really just restrict or take we basically take the canonical surjection out of R. So R decomposes, R goes from x cross I to x cross I. Okay, we decompose R to be this image of R, to this image of R. We include the image of R into the codomain x cross I, and we call this map, this surjection that we factor out of R, to be R dash or R tilde or whatever, R real. So we have this map R tilde to this union, and we have this union, this map from the union to Y, which is phi, and therefore we can compose these two maps, and what we get in the end is really the map we are after. Okay, I drew it a bit too far. You can compose these two maps, and this is really the map we are after, which is G. So we define G to be phi composed with this copy of R, and we claim that G is that homotopy. Why is that the case? So if you look at the definition of the homotopy extension property, we required that there is a homotopy G, but it has to follow us a few conditions, like G restricted to 0, or the first map of G is equal to this map we had from G right here. We had here this map G, this map G, and G basically agrees homotopically to this homotopy F. So G, first of all, we have to show that G, the first map of G, is equal to this G. This is the first thing to show. And the second thing to show is that G restricted G restricted to A cross I agrees or is equal to this F. So, okay, that is a big sentence right there. Let's try and break this apart one by one. We have that map F. Okay, first of all, what is G restricted to some subspace? What is this map? This map is always, let's say, G is from where? G is from X cross I to Y, and we have this subspace of X cross I, which is A cross I. We have that subspace. There is the canonical inclusion, and here is G, and this thing right here, that is G restricted to A cross I. So this is what a restriction of a map really is. Now looking at this from this angle, we see that this canonical inclusion, if we compose that, we really get that okay, do we really get it? Yeah, we do really get it. That is because focus on this part of the diagram. What is going on here is that we have here A cross I. We have here A cross I. We are injecting it to X cross 0 union A cross I. We are injecting it to X cross I, but we also have the canonical inclusion of this, which is the same canonical inclusion that I drew over there, like X cross I, and we have the retraction R, and there is this canonical inclusion, which is the image of it, is the image or whatever thing that that image of R, which I'm not willing to write right now. We really have this canonical inclusion right here. So we, let's say this, call this J, this is J, this is J dash, whatever, this is, let's say, by whatever naming we are having here, this should be J3. So we really have a triangle of commuting, basically a commuting triangle of, okay, someone is out here. This sound is clear. What's a CW complex, by the way? Okay, sorry I missed that. A CW complex is okay, the CW complex. What is a CW complex? We don't really need it right now, and when we will be proving this thing, we will have a small look at what a CW complex is. Okay, sorry, I missed the chat right there. Anyway, also thanks to Alcaraz. So we really have a commuting triangle of canonical inclusions. Okay, the things are getting more and more grim right here. Anyway, so we have this surjection, and we get this, right? So we see that this inclusion J dash is really equal to J composed with J3. And what else do we know? This is J3. This is the inclusion J right here that we are talking about. This is J dash. That's a lot of arrows in one diagram. Also, are you hello, are you present or something? I guess this happened a long time ago. Yeah, he really just dropped the text and left. I'll fetch him. Just wait a second. Okay, whatever, let's continue. So we know that this map J dash is J composed with J3. What do we want at this point? We want that J dash composed, not J dash composed, rather G composed with J dash, we want that to be equal to F. Okay, we know that phi composed with J3, we know that is equal to, we know that that is equal to, I guess, oh god, phi composed with J3, that is equal to F, we know that. This is what we know. We know that phi is equal to phi composed with J3 equals F. What else can we do about it? We know that G, okay, right. G is equal to phi composed with R tilde. Now one thing you have to notice is that this is one part of this diagram. The other part is when you take that image of R, whatever that subspace is, I don't really want to write it. If you put it into this space X cross I, and if you apply that surjection to get back the image of R, this is really the identity. So really this, not J, this is this J? Yeah, this is J. So J is really a right inverse of that map. So J is really the right inverse of R tilde. This is identity on whatever that space was, image of R, let's say. So we apply J on both sides. We compose with J, both maps. We see that phi composed with R tilde, composed with J. Composition is associative. We can do all these bracket things. And we know that J composed with, or R tilde composed with J, that is equal to the identity. So this is really just phi. Okay, good to go. We are looking good at this point. So G composed with J composed with J3, that is equal to phi composed with J3 equal to F. Okay. And what is J composed with J3? That is precisely J dash. So G composed J dash is equal to F. And as we saw, by what really a restriction is, this restriction is really just G composed with J dash. And that we saw is equal to F. Therefore, the second part of it is done. We have it that this homotopy from the bigger space X cross I to the space Y really agrees with whatever homotopy we had from A cross I to Y. So that is one part being done. Now the other part of this business is that we have to show that the first map of it is G. Now what does it mean to get the first map? What is really this map right here? Let's see. What is this thing in terms of these maps and inclusions and all that? Notice this one thing, that if you have a map homotopy, which let's call H to Y, and the first map is really map like this. So you take a map, this is H naught, and you include it, you apply the canonical inclusion right here. So this inclusion, what this inclusion really does is, it is basically a product with the identity map. So what is this inclusion? J right here. J equals this identity on X. First of all, we product that with this inclusion map of 0 to I, so whatever that is, J sub 0, let's say. So that is what the inclusion is. And from this, since this triangle commutes, as you know, something happened. Okay, nothing happened. Anyway, so we see that h naught, which is basically the first map, like this, it is equal to, again, a composition of an inclusion with that homotopy. So that is what really the first map is. So what now we have to show that G, what is the first map inclusion? Which inclusion are we talking about this time? We are talking about this inclusion. Okay, that will be real gymnastics, but we are talking about this inclusion along this path. We include x cross 0 into a cross I along this path. This is the inclusion we are talking about. So what is this inclusion? Last time we had an inclusion, a j dash, and the j dash was really j composed with j3. And now the inclusion we are talking about, let's say, let's call that j double dash. The j double dash inclusion is j, again this inclusion of this union space, j composed with j4, I think that was the name. Yeah, let's just name these. This is j1, j2, this is j3 already, and j4. So yeah, have a look at this diagram properly. So all we are doing in this proof is playing around with that diagram, and it all works out. So what we really want to show is that G composed with J double dash is equal to this map G tilde right here. Again, this was supposed to be something like G actually, but since G, there is homeomorphism right here, so we really should not worry about it anymore. If you want, we can really have this bigger. Yeah, let's have this one. We are taking this inclusion, J double dash. Let's call this homeomorphism H for the lack of a better name. Okay, what am I proving? That is a good question. We are doing this from a long time now, and that is, we say that this is the theorem. This is the theorem right here. X comma A, this pair, has the homotopy extension property. That is not a W actually, I just noticed. There is an H. Has the homotopy extension property if and only if X cross 0 union A cross I, whatever that space is, it is a deformation retract of A cross I. So yeah, that is in a nutshell what we are trying to prove. And for the homotopy extension property, the definition of it, this is the definition. You can also rewind back in the the stream. Yeah, this is what we are proving. And to have a brief of what, yeah, this is a good time to have a brief recap of, okay, what does this say intuitively? This does not say anything intuitively. That is the problem, that you cannot have this space, and there's no good intuitive thing to about this space. You can have a look at a few examples. You can look at an example. Yeah, you can just look at an example what this space looks like. I'll just give a small example right here. Suppose your space X is this circle, and your subspace A is this point, for the lack of a better example in my mind right now. This is the cylinder on the circle, which is basically this A cross I, and this is let's say we make copies of this. X cross A cross 0, this is A cross 1, this entire space is A cross I, this is X cross 0, this is X cross 1, And this line right here, this entire line is a cross I, and this circle is a cross 0. So we are saying that this cylinder, this pair, this circle and this point, this pair has the homotopy extension property if and only if this entire cylinder deformation retracts onto whatever the combination this circle and this line makes. So if the cylinder deformation retracts to this thing right here, that is what we are really after. Yeah, this is algebra and topology. Yeah, this is basically algebra and topology. Okay, we can do that apparently. Anyway, so that is what we are after, kind of. Anyway, if you want to have a, okay, let's have a brief of the proof. So what we are trying to do here is we are trying to show the converse direction. First of all, this proof will take some hours as far as I'm like predicting this. This has been going on for a long time now. So how to make sense of this huge, ginormous, weird looking space? At least the name is super weird. This is x cross 0 and a cross I, and there one way of looking at it is as it is a union of two spaces. So we take the two spaces x cross 0 and a cross I, right? A cross I, and we can include them into the space. Now one thing is, this kind of a inclusion diagram, it really works because it really works when we are taking a disjoint union or we are taking a coproduct. So this is kind of like a coproduct diagram. Almost, this is almost a coproduct diagram. But there's one catch, is that we are not really taking a disjoint union here. We are just taking the usual traditional set theoretic union. So for that, we also have to account for the intersection that is present between the two spaces, which is a cross 0. Now since you can like include 0 canonically into I, because 0 is that set 0, the singleton 0 is a subspace of I, and you can also include A, the subspace A, into X in a canonical way. You can therefore include A cross 0 and what is this? Yeah, you can include both. Yeah, you can just cross it with the respective spaces. You can include A cross 0 into X cross 0 like that, and you can include A cross 0 into A cross I like that. So there we have the main proponent of this proof, which is this commuting square. So that is what is really going on. So we are taking this commuting square and we are taking properties out of it and hoping that it proves something. What else we are doing with this commuting square is that we have two things. First of all, X is homeomorphic to this space x cross 0. This x cross 0 is a copy of this space X, and also that x cross I contains this space a cross I. Okay, so we have a few things here. The commuting square of something which is really best called the fibered coproduct. We also have the homeomorphism X along with x cross 0, and we also have a third thing, which is a cross I can be included into x cross I. Okay, sorry, I made a mistake here. We are not really after that inclusion of a cross I into x cross I. We are after this inclusion. We are after this inclusion, that this thing right here, this can be included into x cross I. So this space, which is, I will just call it something, let's call this L. This is really pathetic space. This L is a subspace of x cross I, and therefore we have canonical inclusion. That is how subspaces are defined, that we have some canonical inclusion. Now, what is a canonical inclusion? A canonical inclusion is just a monomorphism. It has no other structure. It is just an injective map. Let's give these maps names. Oh god. Let's call this J2. This is J4. This is J. And you can compose the other maps in this and get various maps, but let's keep the diagram simple because it is already way more cluttered right here, so we don't want more clutter into it. So this is still a brief of the proof. We are just having a brief of the proof, and what we know is that this space not only is a subspace of x cross I, this space L is also a deformation retract. So we have a retraction going on, this retraction R tilde. So x cross I retracts onto that subspace L. And we know from this we can have this important thing, and we have here that what was it? It was that wait a second. Yeah. So this J composed with this retraction, this whatever, this restriction of retraction or whatever you call it, that was the main retraction R, because this is a deformation retract of the space x cross I, and the fact that R tilde composed with J equals the identity on the space L. That is all part of the definition of a deformation retract. So where was the deformation retract? It is way up here. It's all part of the definition of a deformation retract, that the homotopy is always identity on the subspace A that we are talking about. So it is all right there. Yeah, so we have that J is a right inverse of R tilde. Okay, so now that everyone who was watching has left, we can continue with the proof. Yeah, so we are basically massaging this diagram right here and getting more and more information out of it, in it. So we have this whatever that is. We have this map, this G right here. We have a homotopy F to Y right here, and what we really want is a homotopy G, such that some things happen. Okay, we can continue proving as we were, to show that G composed with J double dash is this G tilde. That is really simple, because we know that, okay, what is J double dash? J double dash, that J double dash is equal to J4. J composed with J4 composed with that homeomorphism H. Okay, now we can go on with this. G composed with J double dash, that is G composed with first of all J, then J4, then the homeomorphism. G composed with J, we know what that is. We know that is equal to phi. Okay. composed with J4. Phi composed with J4, what is that? Phi composed with J4. Wait, where was it? Jeez, man. Phi composed with J4. That was the map from x cross 0 to y, which was that was the map from x cross 0 to y, which we know was, yeah, this is G composed with H, which we know is G. So we really see that G composed with J double dash is G. That is the first map of G that is really equal to G. And we already showed that G agrees with this homotopy F. Therefore, we have proven what was that? MMM monkey. Okay. So we have proven finally this direction of the proof. So we really know now that if this thing is a deformation retract of x cross I, then the space really has homotopy extension property. Okay, so we really proved this direction. I guess we will take a break for a few minutes and then we'll be back proving the other direction, that x comma a has the homotopy extension property. If x comma a has the homotopy extension property, then that space is really a deformation retract of x cross I, which I guess will be, well, not as routine and straightforward as this direction of the proof. So we are coming back and showing this. Suppose x and a has homotopy extension property, then we show that there is a deformation retraction, retraction of x cross I to whatever this monstrosity is. Yeah, we will come back and show this.